Right, folks, we should get started. Um, just it looks like a lot fewer people are showing up uh, exactly on time, but thankfully the class is streaming on YouTube, so and there is the recording available. So we'll start with our uh, lecture as always. So um, just a few reminders before we get started. Homework one is due today, um, but in case as a general policy, I've decided that for this homework and this homework alone, I'll waive the late penalty um, if you submit tomorrow, and that's pretty much it. There won't be any more extensions after that. Um, and as I said, maybe multiple times now, this is a homework that can be heavy. So in case you haven't yet started, after class might be a good time to start. You might still make it. So do and the other thing is, if it's any infrastructure code that you write for this homework, any sort of um, cross validation and even your decision tree code and such things would be helpful for future homeworks or maybe your project. So don't even though this might take a lot of time, I have been told that as the semester progresses, the amount of coding, for example, that you may have to do tends to go down in the homeworks simply because you end up reusing your older code or maybe even fixing your older code uh, as you go along. Please do use Canvas for discussion. There's a lot of discussion there. Um, and if you have a question, there's a good chance that someone's already brought it up. If nobody's brought it up, then maybe you should bring it up. There aren't any updates yet on the project. There are some technical issues involving the data set that I'm still trying to resolve. So I'll move the milestone that's supposed to be there next week. I'll move it so that you get enough time to actually look at the data. Um, are there any questions about the homeworks? I see there's a question about the waiver. I've already talked about that. Yes, there will be the late penalty for will be waived if you submit tomorrow. Are there any other questions? When will homework 2 come out? Yes, the plan is it'll be late today. I hope we stick to the plan. If not, it'll be there tomorrow morning. And homework 2 will involve you thinking about linear classifiers and maybe proving something about the mistake bound model, which maybe we hopefully will see either both today and on Tuesday. And the programming part of the homework will involve the perceptron algorithm and many of its variants. And as those lectures go along, you'll be able to do more and more of the homework. So hopefully we'll have homework 2 out either late tonight or tomorrow morning. I can see you're eager for more homework, so that's good. Let me move on with the announcements. Actually, the next two things are just advertisements that I would like to just inform you. Uh, I don't know how many of you are aware, there is a data science club. The University of Utah has a Center for Data Science, and a part of that, there's a student-run data science club, which is whose activities are entirely, in some sense, controlled by the students of the club. Occasionally, some of the faculty show up and just hang out, but it's really a club for the students. If you're interested, if you're interested in being a part of this group, all you have to do is go to this website. And if you don't really want to look at the website, you can just search for Utah Data Science Club online. And I've been told to inform you that there's a social tomorrow on Scribble, some online game thing, at 4 o'clock. Anyone who's interested, please do show up. I've been told it's a fun place. You don't have to, it's a mix of grad and undergrad students, and There are various kinds of activities, tutorials, and presentations from people from the industry and people from other university students, mostly from other universities. Um, there's also plans for some sort of a longer term hands-on group project that people are going to just create by themselves, and the students are going to make by themselves and manage by themselves. So if you're interested, please check out Utah Data Science or datascience.utah.edu/club, or just search for Utah Data Science Club. There are every Friday has seminar talks, and there is this Discord link here. I'm not entirely sure what that does by being on the slide, but you can find all this information on the website also. Another advertisement is about a career expo. This is primarily for computer science or computing students. There's a career expo next Friday. I'll remind you again next week. If you want, it's called Pathways. If you want to know more about it, go to cs.utah.edu/pathways. I'll occasionally keep making these kinds of advertisements and announcements as we go along. And this is maybe hopefully an incentive for you to come to class at 9:10. Any questions or any logistical things that you would like to bring up? If not, if there is no will homework one still have a late day? No, it will not. Tomorrow is the late day, and it will not have a late penalty. So today is the official due date. Today is the due date, and the late day is tomorrow, and the late penalty for homework one alone is 0. Does that answer your question? Any other concerns? I hope most of you have at least started the homework one. If you've not done this kind of stuff before, as I said, it may feel a little daunting. And if you feel that, it's a perfectly normal thing. All I can say is that as we go along, the homeworks will feel easier. There'll be the same amount of work, they'll just feel easier. And the other thing is that, the amount of work you put in for this homework will help future homeworks also and your project. The other thing I wanted to mention about this homework is runtime. A few of you kind of hinted that this is taking forever to run. It should not take a very long time. It should not take hours. The whole homework should run quickly. If not, you might want to rethink how you've implemented decision trees, because that could be a point of inefficiency. It's and even if it runs efficiently and you've got everything working and you would like something challenging, think about how you would make it more efficient. So there's a question about the CSV for the training data had way more lines of data than the original train file from the assignment, and that one took forever to run. I will one of my TAs will look into that. I think Mattia, you can probably just check that out, or maybe we will look at that after the class today. The difference between the CSV file and the libsvm file really is, are we representing the zeros or not? If a feature has a value 0, the libsvm file says, I'm not going to show, I'm not going to put that in the file. The CSV, so it's basically a pair of key values. The key is a non-zero entry and the value is the value. And the CSV file consists, basically puts down all zeros also. That's the only difference. They should be the same information. If not, we will take a look at it. What would you expect? Another question, what would you expect a decent runtime to be? Now, this depends on what language you use and how you implement things. I think when I implemented this a little while ago, meaning when I implemented a decision tree a few months ago, just for fun, and played with a data set of a similar size, learning would complete in the order of minutes. Maybe no more. The whole experiment would take no more than 10-15 minutes tops. And this was in a very inefficient, hacky code that I just put together. So it should not take too long. I mean, but too long is a subjective thing. Minutes, a few minutes, 15 minutes is considered to be super quick in the machine learning world. Just as an aside, I'm aware of certain learning algorithms that certain learning programs, even without cross-validation, just straight up learning takes order of weeks. So, minutes is nothing. For testing, will the libsvm be used? You mean for grading, right? If no, I mean, if you've implemented the libsvm thing, we'll have both files in the same directory and just run it. Your code should pick it up. Are there any other questions? John asks, all this data set is all numeric. Should you expect the same for future homeworks, or might we experience strings? You will not experience strings, simply because anytime it's a string, you can always convert it into an index. So, and this is the standard operating procedure for strings. So if you have a string, let's say we have a collection of strings. I'm going to write some example here. So let's say you have cat. So let's say you have these 3 strings. What you would do is you would put them into a dictionary of string and integer. So you'll have 0 is cat, 1 is dog, 2 is hat, and it keeps going. And if I have a feature for the word cat, what you would convert it into is you'll say that the feature ID is 0 and the value is 1. Basically, strings get converted into integers because all they end up being indices in a big feature vector. This is the standard operating procedure. I think I spoke about this when we were talking about vectors, features as vectors. Any categorical feature will get converted into indices. Michael asks, when logged into so NumPy is not installed. Right, so this is something that just came to my notice recently. Apparently the Windows skate system and the Linux skate system have different Python installs. So I'm going to ask you, just as a default, assume that NumPy will be installed, the latest version, and Pandas will be installed, and just use it. We will make sure that your code works, whether it's Windows or Linux. If you are comfortable working on the Linux, just use it, Windows or whatever. Do you want the output values? So another question is, do you just want the output values from the run.sh, or should we label the values? I don't understand the difference. What do you mean by labeling the values? Root feature is 4 or just 4? Oh, you write the root feature. I mean, so that we know what it is. Just assign the labels. Just make it easier for us to understand the output. So yeah, use the label. I mean, write the first one. Nitin asks, for the depth of the train tree in problem 1, will we be looking for a specific range, and different implementations get different depths with the same accuracy? So this is a question that keeps coming up multiple times. So in general, in general, the accuracy, okay, let me talk about specifics first. For decision trees, there's very little randomness in the process. The only place where randomness comes in is if you make a random choice for In case the information gains are equal, you choose a certain feature to split on or another randomly. And that way, two different runs can be random. Otherwise, everything here is deterministic, so you should essentially get the same tree. But there's a small chance of randomness in the sense of in what I just described. In As we go along in future homeworks, and also in general across machine learning, different runs of a learning algorithm do produce different models. Why? Because we're talking about, so as we will see later on, a lot of machine learning can be treated as stochastic optimization. And what that means is that there's a certain there's a certain amount of inherent randomness in any learning algorithm. As a result, different runs will produce different classifiers, and different classifiers could produce different accuracies. So we will not be looking for, I mean, admittedly, as I said, for decision trees, randomness is much more controlled. However, as a general policy, I won't be looking for exact numbers. I'm not entirely sure you get a big change in the depth. There might be minor differences, but I won't be looking at exact numbers. You'll Instead, we'll be looking at two things. We have our own implementation of the tree, and we have a sense of what the accuracy would be and what the depth would be. And we also can get a sense of what the class average accuracy is and what the class's average depth is. If you are too far off from these two numbers, we'll penalize your results. For example, if you are more than one standard deviation or even more, we have to decide the boundaries. If you are too far off from the class mean for accuracy or error, that suggests that there's something wrong. And this could happen both ways. If the average accuracy that we got and the class gets is say 70%, and your classifier gets 95%, that immediately suggests something's wrong. It seems like it's a very good thing. Accuracy is 95%, but from the point of view of this particular learning algorithm, if it should not get 95% and you got it, that suggests a bug. So that will get penalized. But if it's 70 and you get 71, it's fine. Does that? I hope that clarifies things. There's another question about whether runtime is important for grading. So, okay, that's a good question. Runtime is, we're not going to measure runtime for grading. We don't care about your runtime within reason. I don't expect anyone who's grading your homework to try to wait for hours for your code to run. As a general rule, if it does not finish running within a reasonable amount of time, and we have to decide what reasonable is as we start running your code, we will stop the code, and we will not wait for hours or days so that the code runs. So that's an important thing. So there is, but other than that, we're not going to rank people by runtime. We don't care. I mean, if it runs, it runs. So runtime is important as long as it is small, as long as it is reasonably small. So there's another question. The experiment, question 3, part 2 said that the experiment with depths in the set 1 to 5, does this mean we need to set the limit for the depth in the set? Yes, when the depth is not limited, the depth could be up to 100, actually 120 something. But we are asking you to only consider these 5 things. If you're interested, I encourage you to try out more. But for the purposes of this homework, this is the hyperparameter choice. Any hyperparameter, you need to come up with some sense of what hyperparameters you're going to explore. And we are asking you to explore depths of 1 through 5. You're welcome to try out more as we go along on your own. And if you find anything interesting, do write about it. We'd love to know. All good questions. Anything else, or we can move to the lecture? I don't see any questions forthcoming. Someone's typing, I'll try to get that. And then in the meanwhile, I'm going to go to the lecture. We're going to go back to where we were. we were in the last lecture on Tuesday, we looked at linear models. Just to remind you, we looked at two kinds of linear models, linear classifiers and linear regression. A linear classifier is a hypothesis-based assumption. It says, when I get some data set, when I'm trying to model a data set for a classification problem, I'm going to assume that the true function, the target function, the positive and the negative points in the data as per the target function are separated by a line or a hyperplane. So mathematically, you might say the label, you're going to explore functions of the type y equals the sine of w transpose x plus b. And in linear regression, there's no sign. So you're going to explore functions of the type y equals w transpose x plus b. Now, both of these, I mean, they are different kinds of problems, but they're both, we'll call them both linear models. The thing is, all of this is an assumption. So why should we come up with this assumption? Why should we even make this assumption? And this is essentially saying, we are making an assumption about the nature of the true concept. And if the set of, if the true function is not linearly separable, then we end up, we will not find the real function. We will actually make our classifier that we learn will end up making mistakes. So this is a hypothesis choice, and every hypothesis choice comes with almost the same sort of assumption. We will search for functions within a set of functions. We will search for the true concept within a set of functions, the hypothesis space. And if we find it, that's good. And we'll try to find the best classifier within the space, or the best regressor within the space. One of the reasons why linear functions are interesting is many different kinds of interesting functions, interesting concepts can be represented using linear classifiers. In the last lecture, we saw how conjunctions and disjunctions can be represented as linear classifiers. We saw that M of n functions can be represented as linear classifiers. And now we're going to see the opposite case. Sure, many interesting functions can be represented as linear classifiers, but that doesn't mean that everything is linearly separable. The most famous example of a function that is not linearly separable is the XOR function or the parity function. In the Boolean sense, the XOR function might look something like this. If you have two features, let's say x1 and x2, and let's say y equals XOR of these two things, you have 0, 0, 0, 1. Basically, it is if both of them are true or both of them are false, the output is 0, otherwise it's a 1. So this is when both of them are false. And what the picture here is representing a similar sort of an idea. So you have pluses here, and you have minuses inside this. And notice that you cannot draw a line that separates out the pluses and the minuses. I mean, this is essentially it's not a, what I've just said is not a proof. You can try to prove it, but this is a rather intuitive idea. Any way in which you try to draw a line that separates out one cluster of pluses from the other minuses, you'll the other cluster of pluses will be in the negative side. So if you draw the line here and say this side is plus, you've given up on this cluster. And if you do the opposite thing, if you draw the line here and say this side is plus, you've given up on this one. And these are pretty much the only options. So the parity function is not linearly separable, and this was actually a pretty big deal. It may seem like a trivial thing to say, but it turns out that in the 1950s, late 50s, there was a revolution in in what at that time was, let's call it AI or pattern recognition or machine learning. It was not called machine learning at that time. The revolution was this algorithm called perceptron, which we will see next week. And the perceptron algorithm was rather simple, and there was this big hype around it until there was a book written in 1969. In fact, this book here called Perceptrons, which basically just said, look, the perceptron algorithm is something that can only learn linear classifiers, and it can't even learn XOR. If it can't learn XOR, how good could it be? Because the XOR function is so simple, it can't learn parity. And this apparently killed off funding for artificial intelligence, leading to what is called the AI winter. So this has the XOR function has a special place in the history of AI. However, even though parity is not linearly separable, by the way, this is not the only function that's not linearly separable. XOR, you can think of it as the output is 1 if the number of ones is, I think it should be odd. But it doesn't matter really. Neither of those are linearly separable. But it's not just this function. Many non-trivial linear functions, Boolean functions, are not linearly separable. This example here is this is an example of a function that is a Boolean function, but that is not linearly separable. I think it's not. I mean, I have to. Maybe I'm almost certain I've made a mistake here, but most non-trivial linear functions, Boolean functions, are not linearly separable. But the thing is, so there is a comment in the chat. Can you linearize XOR in X, and in this example, in X and O? This is so wrong. It's not Y equals X or okay, this is wrong. So let's just cut this whole thing. I'll fix it when I post the slides. This is Y equals X1 XOR X2, which is X1 and not X2, or not X1 and X2. So this function is not linear. It is not linear in X1, X2. What this means is that there is no W1, W2, B such that the sign of B plus W1, X1 plus W2, X2 is equivalent to the XOR function. And that's what I mean by it's not linear. It's not linear in the feature space that we are given. However, to kind of continue on this comment from Anthony, even though these functions are not linear, they could be the feature space itself can be transformed so that in the new feature space there is a linear function. So let me show you an example. So these points, so let's say we have points lying on this line. So our instance space is the one-dimensional space of X here. Every example is one of these dots. And what we have here is we have circles here, and pluses here. And our goal is to separate them. And we can try to separate, we could ask, can we separate them with a one-dimensional line? A one-dimensional line is an interesting object. It's nothing more than a point. So a one-dimensional line is a point. So what that means is this question is asking, can I put a separator anywhere such that, and mark one side as plus, such that I'm always right? And you can, just by enumerating, you'll find that if I put the separator where it is shown, it's and say this side is the plus, then these points are mistakenly classified. And if I do the same thing on the other side and say this side is a plus, then these points are mistakenly classified. So this data set is not linearly separable in its original space? And the answer is, who said you have to remain in the original space? We can transform the feature space however we want, because we get to, it's part of the model design. So we change the representation. Instead of, and in this case, in this particular case, we will use what are called feature conjunctions. We will take the feature, the original point x, and convert it into this space, x comma x squared. We'll convert it into two-dimensional examples that look like this. So we originally had points only on the line. We have deterministically transformed these points into this new representation. Each point, this point that was -2, has now become -2 comma -4, and this does not require any new data. I know how to compute x squared. This is just a design choice that I have made. I'm going to say, I'm saying here that perhaps in this quadratic space, these points are linearly separable. And of course, yes, in this new space, I can draw a line that perfectly separates out all the pluses and the dots. This notion is, this idea is sometimes called blowing up the feature space, where we just consider all possible combinations of the features in order to construct a new representation where the data might be linearly separate. So many points can be separated in the many data sets that are not linearly separable can be separated in this sort of a transformed representation. There is a technical, a tiny question, a point of order that we need to consider. How on earth are we going to figure out what is a good transformation? Here, I can see all the data points, and I see that, there are minuses on this, or circles on this side and circles on this side. If only I could just bring the circles up a bit, then I can draw this line. If I can take all these circles here and these circles here, then I can draw, and don't do anything to this, then I can draw a line. So in order to separate out these things, I have invented this feature transformation that's here. How could you invent this feature transformation? There are two ways to go about this. One is to think hard about the problem and write down the answer. Of course, that's not always easy. It requires expertise. It requires understanding the data. It requires understanding the domain. Another way of thinking about it is perhaps we can learn these feature representations. Can we learn these transformations from data? So now we are not only learning the classifier that separates these things, but also learning that this point should really be mapped to this two-dimensional point. This notion of learning representations is a fundamental conceptual component of modern neural networks. In some sense, that's really what they're doing. And I'll revisit this point when we discuss neural networks. But this is a very simple example of a handcrafted feature transformation. You'll be doing some handcrafted feature transformations in your homework also. You'll be exploring this a little bit. And as an exercise, I want you to think about how to use feature transformations to make XOR in 2 dimensions that we saw before linearly separable in the new space. In order to think about this, you have to think about a function that maps examples from this 2-dimensional space. So just to clarify, I have these 4 points. This is 0, 0. This is 0, 1. This is 1, 1. This is 1, 0. And the XOR function says this is a plus. No, yeah, this is a plus, this is a plus, minus, and a minus. The goal is, how do you wrap the space around, just like we did with that line? How do you wrap the space around so that all the pluses go on one side and all the minuses are left on the other side? And you can, it's up to you to invent these feature, these sort of feature transformations. It doesn't always have to go to a higher dimensional space. It could move to a new 2-dimensional space. And there are some suggestions in the chat. We can combine features. Yes, that's perfectly right. But let's consider two kinds of combinations. If you consider x1 plus x2 versus x1 times x2, the first one is still a linear combination of these things. So it does not add any non-linearity to the system. So it might not work. X1, X2, on the other hand, introduces a degree 2 term. You're essentially building polynomials here. And that, I mean, I'm going to ask you to play with it and see if it works. Christopher has a similar suggestion. So I'm going to ask you to think about these points, think about these suggestions that are on the chat, and explore this. And we can come back to this at the beginning of the next lecture if you have any questions, or we can talk about this in office hours. Oh, you are not allowed to use XOR. So that's a good suggestion. There's another suggestion in the chat that says, what if I use XOR as a feature transformation? Of course, that will work. If you use X1, why do you need X1, X1, XOR X2? You can just use the target concept itself. However, while that will work for this case, in general, it will not work because you don't know the true function. So I want you to think of building blocks that you can use to build the XOR rather than you building the XOR itself, rather than using the XOR itself. But that's a clever suggestion that even for the homework, there will be questions around this where you're supposed to invent some feature transformations, and you're not allowed to use the target function simply because otherwise it's a trivial thing. All right. The other reason why linear classifiers are interesting is because many data sets, especially when the dimensionality becomes very, very large, end up becoming almost linearly separable. They may not be perfectly linearly separable. And for example, in this particular slide here, I don't think there's a way to draw a single line that separates out the pluses from the minuses perfectly. You could try all these things, but it really won't work. But it's almost linearly separable, so you could maybe live with the error, live with the mild inaccuracy. So instead of getting a perfect 100% separator, you get like a 95% separator, and maybe you decide that for your problem, this is fine. So especially in very high dimensional settings, data tends to be more linearly separable. This is a loose statement, but it's almost right. And in practice, we can end up with extremely high dimensionalities. So for example, as recently as a couple of years ago, I was playing with a data set where the dimensionality, because we invented a whole bunch of features for the task, the dimensionality ended up being roughly of the order of 1 million or 2. And the sparsity, then we had million dimensional vectors with maybe no point being more than 300 non-zero entries. It's extremely sparse, extremely high dimensional, and linear tends to work, data tends to be reasonably linearly separable. What you need to think about in these settings is how much noise are we willing to live with? And again, it's a domain question. So we can draw these things, and now the thing is, linear classifiers are an expressive hypothesis class. Many functions are linear. As a result, it's a good guess or a good first thing to try when it comes to guessing a hypothesis space. It's always important to know that some functions are not linearly separable. A classic example is the XOR function. In fact, a lot of in many machine learning questions, a counterexample ends up being the XOR function. So it's a fun function to keep in mind. And most non-trivial Boolean functions are not linearly separable, but we can make them linearly separable by applying these feature transformations. One minor final comment before we start wrapping up this unit. A question comes up often: why do we need this bias term? And I briefly discussed this on Tuesday also, but I want to spend a little bit of time on this. So this bias term B is crucial, because if you miss the bias term, you will not be able to separate out these two class of points. Essentially, if you miss the bias term, you are saying that you're only going to restrict yourself to lines or hyperplanes that go through the origin, which means you are restricting the hypothesis space a little bit more than necessary. And this is something that is very easy to forget. So it's always important that you make sure that there is a bias term explicitly or a bias feature. So you could have a feature that is always one. So you have W0 plus this thing. And that's exactly the same as saying W0 times one plus this, where and you add a bias feature. So it's important to add a bias feature. And this is I say this with aware of the fact that it's easy to forget to do that. Some libraries would be, some libraries would insist that you have to introduce the bias term um, explicitly. And if you forget to do that, you will, you might end up getting bad performance. So this is something you should keep in mind. There's a comment. You can transform the data points by translating, by essentially moving this thing up a little bit. And that's equivalent to a B using B. Yes, that's right. But how do you know how much to move? And why do you want to move it as a pre-processing step when you can actually learn how much to move as part of the learning process? So the learning algorithm will do it for you, will do the transformation or this translation for free. So why do that extra step unnecessarily? But essentially, you're right. If you do translate the points so that you don't have points going through the origin, then you're okay. But I think that just adds extra work. It's much easier to just add the bias term. But that's a good observation. Yes, you're right. Are there any, so another question is, are there real world problems where it's more efficient to restrict yourself to hyperplanes which go through the origin? I don't think so. I mean, I can't comment on all real world problems, but in general, I don't think it's going to matter, simply because all you do with the bias term is add one extra parameter. One parameter is not going to cost you much. Originally, if you had D parameters, now you have D plus one parameters. And that's not a big deal. The even if the real hyperplane does go through the origin, I would like the data to tell me that rather than me guessing it. So you don't see any computational advantage of restricting yourself to go through the origin. And in fact, if you really want your hyperplane to go through the origin, imagine yourself in this D plus one dimensional space where the term with the hyperplane with the bias does go through the origin. So there is there's not much of a difference. So I personally, I don't think there's any reason to avoid the bias term. All right, so this is the end of our unit on linear models. As an exercise, I would like you to do a few things. First of all, write down the simple disjunction as a linear classifier. And if you want, you can find the answer on the slides. And the next one is, how do you think about how you might apply the feature space transformation idea for the XOR function? Once again, I think the answer would be on the slides if you or not. If you want to discuss it, come to office hours and we'll chat about it. At this point, I'll pause and wait for questions while I find my new slides and take a sip of my tea. We're going to change gears now. I don't see any questions coming up. So there's a very good question. Did we go over how to learn the weights? Now that's an important question. I talked about what linear classifiers are and what they express, and pretended that. I talked about what linear models are, and I talked about what kinds of functions they express, but I never really spoke about what class of, what kind of learning algorithms there are. At the end of somewhere in the towards the latter half of the previous lecture, I did kind of give a hint. So there are many, many different algorithms for learning linear classifiers, and we'll be spending a fair amount of time going over that. So just to kind of list out a bunch of names that you will see in the over the course of the semester, the perceptron algorithm, the grand old daddy of these things from the 1950s, learns a linear classifier. Support vector machines learns a linear classifier if you don't do anything fancy. Logistic regression learns a linear classifier if you don't do anything fancy. Naive Bayes, in with certain assumptions, learns a linear classifier. And there are we will cover these four, and there are a few more algorithms also where essentially the decision boundary is linear. So we'll cover a whole bunch of learning algorithms that for learning the weights, the parameters of a linear classifier. And that's going to keep us occupied for many weeks. But it's a good observation that you noticed I didn't talk about that. All right, so what we'll do now is switch gears a bit. We spoke about linear models, and now I'm going to switch gears and talk about something more abstract. Before we go into concrete learning algorithms, we need to think about what does it mean for a learning algorithm to be good? And is this even a well-defined question? And how do we go about thinking about this question? How good is a learning algorithm? So the answer to this question really, as we'll see in a minute, depends on how we are going to set up the learning game and how we are going to define success. And different ways of doing, setting up the learning protocol and different ways of defining success lend themselves to different learning algorithms. And the reason I'm bringing this up is because this will be our segue into a class of learning algorithms called online algorithms or mistake-driven algorithms, which are a special case of that. So let's get started with this, and we'll talk about online algorithms in the next lecture, most likely, or maybe we'll start a little bit. So the goal is to rigorously quantify the performance of a learning algorithm. So imagine that someone comes to you and says they have this magic learning algorithm. It can learn anything. It can do it. It's fantastic. How do you believe them? How do you prove, or what questions do you ask them that will convince you that their learning algorithm is good? And it doesn't have to be someone else. Imagine that you invent a learning algorithm tomorrow. What questions would you ask yourself that tells you that this learning algorithm is good or bad? It depends on how you define good and how you define success. One approach, and this is the one that we will use with for quite a bit of the semester, is to ask how many examples should the algorithm encounter before the learned hypothesis is good, or how many examples should the algorithm encounter before the learned hypothesis is good enough. And you can think about why this question is this approach is interesting. This approach is in some sense quantifying the efficiency of the learning algorithm at distilling or discovering the concept from data. But this by itself is, while this may seem like it's a reasonable approach, it turns out this number is by itself insufficient. The number of examples that a learning algorithm sees actually depends not just on the internal mechanics. The number of examples it needs depends not just on the internal mechanics of the learning algorithm, but also on the way in which the learning algorithm interacts with the true function, with the oracle, or with the concept, or with nature. So this is what I'm going to spend a little bit of time talking about, because this is something that we'll not touch upon in too much detail, but it's an important thing to keep in mind, because the number of examples that a learning algorithm needs crucially depends on how it interacts with nature. So I'm going to use conjunctions as an example to illustrate this point. So let's say that there is a hidden function a monotone conjunction that the learning algorithm, let's say you're the learning algorithm for now, wants to learn. And let's say this is the true function. The true function, there are 100 features in our problem, but let's say the learning algorithm does not know that which of these features are relevant, but the oracle knows, the teacher knows that the function is basically says the output is true if x2 and x3 and x4 and x5 and x100 are true, and only when all 5 of them are true. So it's a conjunction, it's the and of all these things. So now we have the following pieces of information. The oracle, the teacher, knows the true function, f. The oracle also knows, so what does the oracle know? And let's think about what the oracle knows and what the learner knows. So the oracle knows f, the learner does not know f. The oracle knows the dimensionality, and the learner knows the dimensionality. And because the oracle knows f, the oracle also knows which features are relevant. And the learner does not know this. There's one more thing that the oracle and the learner both, we are going to assume, knows for the purposes of this conversation, which is both of them know that the true function is a monotone conjunction. So let's say just to simplify things, let's say both of them know and agree that the true concept is a monotone conjunction, and the goal of the learner is to discover which function it is. Now, in order to efficiently discover this function, and by efficient I mean how many examples are needed, we can't really say how many examples are needed without actually saying how the learner interacts with the oracle. So let's consider 3 different protocols. The first one is called active learning. In active learning, the learner asks questions to the teacher. And in this case, we are going to, once we start talking about asking questions, the questions could take any form. We are going to restrict ourselves to very specific kinds of questions where the learner picks out, carefully selects examples and gives it to the teacher and says, what is the label for this one? So essentially, the protocol is always the learner gives an example to the teacher and the teacher says, here's the label. And we can ask how efficiently can the learner discover the true function? Another protocol, we'll call it teaching, where is the one where the teacher carefully selects training examples and gives the smallest number needed for the learner to discover the function. It does not give any wasteful information. The third protocol is the standard setting for supervised learning. There is a random source, nature, that selects examples. Neither the teacher nor the learner get to control which examples are labeled. A random source selects examples, and the teacher gives the labels for these examples. So both the learner and the teacher get to see which examples there are, and the teacher gets to label a bunch of them. So let's maybe go into a little bit of depth about each of these protocols. And the punchline will be, depending on which protocol you use, the number of examples needed for a reasonable learning algorithm, any reasonable learning algorithm, will drastically change. And I can prove it to you. So the first protocol is where the learner proposes instances to the teacher. What that means, this is active learning. So and the goal of the learner is to discover the concept as quickly as possible. You can think of this as a puzzle or a game for the learner. The learner wants to find the concept as quickly as possible by asking as few questions as possible. If the learner chooses the queries carefully, then every single query will force the teacher to reveal something the learner did not know. And that should be the goal of the learner. The learner's goal now is to find queries carefully so that every time it asks a question, it picks up new information. And it's actually fairly easy to construct a situation where construct a series of queries where this happens. The learner knows, remember, that we are after a monotone conjunction. A monotone conjunction, in case you are thinking of what that means, is a conjunction, meaning there are a bunch of ands. You're allowed to use and. So maybe x1, x15, and x31. But you're not allowed to use not. You're not allowed to use negation. No feature is going to be negated. You're not allowed to use or and not. You're building a function using only and. That's the monotone conjunction. So we are after monotone conjunction. So then, and let's say that the teacher, the learner knows we're after a monotone conjunction in 100 dimensions. So there's a suggestion that says you set everything to true, and then you set each variable false one at a time. Essentially, this is what is going to happen. We're going to go through, but we don't need the first one, as I'll point out. So let's say the learner asks, what's the label for this particular example? This particular example is a 100-dimensional data point where every feature is true except for the last one. Now, because the last one is an important feature, when that particular value is absent, when that feature is absent, when that is false, the full function becomes false because it's the and of all these things. So the teacher says, yeah, this example is false. The learner's conclusion, because it has constructed this query carefully, the learner's conclusion is x100 is part of the true function. Just with this one example, the learner has discovered that x100 is part of the thing. As a side note, in general, for this particular part of the class, I'll be using 0 for false and 1 for true. This might seem like an obvious thing. In the next lecture, when we talk about, not in the next, but 2 lectures from now, when we talk about the perceptron algorithm, I'll use -1 for false. So when we're talking about Boolean functions, I'll use 0 for false. When we're talking about linear classifiers, and in general, real valued functions that operate in the space, I'll use -1 as false. And this is a deterministic change, and the context will make it very clear. In any case, so what we have here is one query, and we've gotten one piece of information. x100 is in the true function. Now, of course, you can ask what happens if why is this conclusion true? If in this case the label is false, if the label is false, that means x100 is setting it to false has forced the whole function to be false, which means x100 is important. On the other hand, if the label were true, consider that this was 1 instead. What that means is the learner has forced this particular feature to be 0 or false, and yet it made no difference to the function if it had been a 1. If it made no difference to the function, that means x100 is irrelevant. So you don't need it. That means if the teacher says 1, that means if the teacher's response had been 1, then the learner would have learned a new piece of information, namely x100 is irrelevant. So in either case, whether the teacher says true or false, something new comes along. Let's continue this game. The next question that the learner could ask is about x99. And the way it constructs this example where all the features are 1 except for x99. In this case, notice that if all x99 is irrelevant here, which means that the conjunction is true because x2 is 1, x3 is 1, x4 is 1, 5 is 1, and 100 is 1. So the teacher will say f of x is 1. And from this, the learner discovers that x99 is not in the conjunction. And this game goes on. You keep going till x2, where the learner sets x2 to false and everything else to true. The teacher says, oh, when you set x2 to false, the function disappears, it goes to 0. So x2 is an f. So the learner concludes that x2 is an f. And then it does the same thing for x1. And it turns out x1 does not force the function to become false, so x1 is not an f. And as a result, after exactly 100 queries, the learner has discovered the true function exactly. So the learner's hypothesis at the end of this process, h, is identical to f. So these two functions are the same. Now, are there any questions before we continue? What if all variables are irrelevant? Can that still be a monotone conjunction? Trivially true. If all variables are irrelevant, that means that the function is always going to say true. So true is a trivial monotone conjunction. Are there other questions about this game? Now, this may not seem like a fancy learning algorithm, but what this illustrates is an important point. It illustrates that active learning can be rather efficient, but it requires a certain amount of ingenuity on the part of the learner. The learner has to know something in order to construct these examples. In this case, the learner knew that the true function is a monotone conjunction. And also, I mean, this may seem like an obvious thing, but the learner also knows how Boolean functions operate. That in order to learn a monotone conjunction, this is the game I should play. Had the true function been something else, the sequence of questions would have been different. In fact, what if the conjunction was not monotone? What if you were allowed not x2 negations in this game? Then I claim, and I'm going to ask you to verify this offline. If we somehow accidentally come across one positive example, the same game will continue. So all we need is one positive example, and then we can continue the game. So we need 101 queries in that case. And I'll let you. It need not be 101 actually. We need a little bit of extra work, but if we can find one positive conjunction, one positive example, essentially the same game will continue. And you should verify this offline. Let me go to the second protocol now. Let's say in the second case, there's a teacher who knows the function, and the teacher crafts examples carefully so that the learner can discover and tells the learner, look, here is the minimum information that you need to find the function. Everything else is extraneous. This is all you need. So now the teacher is going to create the examples. And I claim the following. The first thing that the teacher would do is give an example of this kind. It will give a superset of all the good variables. So what it does is it constructs an example where x0 or x1, the first feature is 0. Then x2 is in the conjunction, so it sets x2 to 1. x3 is in the conjunction, so it sets x3 to 1. x4 is set to 1. And x5 is set to 1. x6 is not in the conjunction, so it sets it to 0. Everything else is set to 0 till x99. x100 is in the conjunction, so it sets it to 1. And it says, look, this particular example that I've created, where there is a 1 in every position that corresponds to the elements in the conjunction, this particular example has a label 1. It might seem like this is enough. In some sense, the teacher has given the function to the learner because it has put a 1 in every place. But this is not enough because it's possible that this is a superset. So this example could have been 1 even if the true function was just x2 and x100. This function would also set this example to 1. So this just tells you that these are the features. Some subset of these features are in the true function. And then the teacher proves that every one of these features are relevant because if it sets x0 in this original example, if it sets x2 to 0, the value became 0. If it sets x3 to 0, the value becomes 0, and so on. If it sets x100 to 0, the value becomes 0. In each case, what this means, by changing one bit in this, the function became false. As a result, we need x2. And we need x3, we need x4, we need x5, and we need x100. And between these set of examples, so we have how many? We have 5 examples here, and we have 1 example here. With these 6 examples, any reasonable learner will be able to discover that the true function is f. If you want to think of this as a mathematical proof, the first step says that these variables are sufficient. The second step says these variables are necessary, so we get a necessary and sufficient condition. And a reasonable learning algorithm would look at these 6 examples and find the true function exactly. So we'll get h, it will discover the true function h, which is exactly the same as f again. Questions about this protocol? So in the case of active learning, the learner and the teacher needed 100 interactions. In the case of teaching, the learner and the teacher needed exactly 6 interactions and no more. So teaching is way more efficient. Unfortunately, modeling teaching is rather difficult, and honestly, that there's precious little work in this space, so we don't know much more. Are there any questions at this point? So one of two things are happening at this point. Some of you might be thinking, yeah, this makes sense. And perhaps a larger fraction of you are thoroughly confused. So please ask questions. What do you mean by good variables here? Do I say good variables? Oh yeah, when I say good variables, I mean all the variables that are in the true function. So the good variables here is x2, x3, x4, x5, and x100. I could have replaced good with relevant. Then there's another question. We don't know the function when we want to train the model. Yes, we do not know the function. What we do know is the space, the set of possible functions to explore. That's right. The next comment really answers the first question, the previous question. This is still assuming that the learner and the teacher have agreed that the true function is a monotone conjunction. Or alternatively, if you don't, if you find that kind of an agreement rather implausible, let's say that the teacher knows that the true function is a monotone conjunction because it knows the function, and the learner has made a hypothesis-based guess, and this guess is somehow correct. So in either case, we are going to assume that the learner knows that the true function is a monotone conjunction. There's another question that says, oh, we skipped the slides on least mean squares regression. We'll come back to this after we finish perceptron, before we talk about learning theory. We'll come back to least mean squares regression. All right, so let's maybe talk about the third protocol. And the third protocol is perhaps the more realistic one. And this is the one that we will play with quite a bit. In this case, a random source, nature, provides the training examples. The teacher, which could also be nature actually, provides the labels. So there are these set of examples that have been constructed, and the notation here is I'm using this angle bracket to denote a pair of example and a label. So there are these labeled examples where neither the teacher nor the learner get to control which examples are labeled. And given this set of examples, we can ask, what can the learner do? What the learner could do, once again, remember, the learner knows we are dealing with a monotone conjunction. What the learner could do is note that it only needs to look at the positive examples. If it looks at all the positive examples, you're left with the 4 examples that are highlighted, these 4. And what is special about the positive examples? The example is labeled as a plus or a true or 1 because in all these examples, every one of these 5 features is true. the example is labeled as a minus means at least one, if not more, of these 5 features are false. So then what it can do is it can look for the common features that are present in these positive examples. It does not know anything. All it knows is that this example, let's consider this one that I'm highlighting. In this example is positive, and yet these features are negative, are false. That means these features that are false are irrelevant in the true conjunction. So every example eliminates a bunch of features by that are false. So by eliminating all the irrelevant features, the final hypothesis that the learner could guess is x1 and x2 and x3, because notice that x1 is present in all the positive examples, x2 is present in all the positive examples, and so on. And the learner would guess that the final function, its guess of the function is x1 and x2 and x3 and x4 and x5 and x100. Notice that the important thing is whenever the output is 1, x1 is present, and this is the reason why x1 is still in the true function. X1 still in the guessed function, in the hypothesis. Notice that it's not in the true function. So the hypothesis that the learner arrives at agrees perfectly with the data, but is not correct. Given this data set, the learning algorithm has only learned an approximation of the true concept. And the question to think about is this good enough? Could this be a problem? Before we talk about whether this could or could not be a problem, are there any questions? So let's pretend that in this toy setting, there is no noise in this data. This is perfect. We are living in a universe, in this fictional universe where there is no noise, just so that we can kind of explore this concept. Just to briefly summarize the 3 cases that we saw so far, we had these 3 cases, right? We looked at protocol 1, protocol 2, and protocol 3. Protocol 1 was active learning. And what we saw was in active learning, we have 100 examples, and we can learn the concept perfectly. With teaching, which is protocol 2, we needed only 6 examples. And again, it was perfect learning. In the third case, we don't get to control how many examples we have. So we just say, use as many examples as we can find, and we have possible error, or let's call it let's call it approximate learning. The first case is slightly tricky because now we are expecting the learner to be able to interact with the teacher and ask reasonable questions. The second case is extremely tricky because in general, we don't have access to a teacher who can actually distill the concepts about these things in the way that's needed. For example, imagine that the concept that we want to learn is recognizing a cat from an image. I can't even begin to imagine how you would construct the examples that perfectly convey this. The third protocol is the one that we encounter most often, and that's the one where we work with whatever examples we have, so we don't get to really control how many examples we have, and we can only guess a function that is not the correct one. So the question to think about is this good enough? From here, we can think of 2 directions going ahead for how good is your learning algorithm. We can analyze the probabilistic intuition. In this data that we had, we never saw x1 equals 0 when the label was plus. Imagine instead of these about 10 or 9 or 10 examples, we had a million examples of this kind, where we never saw x1 equals 0 when the label was plus, when the label was true. Maybe nature just does not provide examples of that kind. Maybe these examples never exist. So we shouldn't worry too much. And even if it does, it's going to be such a rare event that the function that we learn is going to be good enough most of the time. And by that, I mean, remember, the true goal of learning is always performance on the future data. Is generalizing to the future. So if we never saw a perverse example where x1 equals 0 and the label was positive in our training data, and our training data was large enough, maybe it's such a rare event that it doesn't happen at all, or it happens so infrequently that it's within our threshold for error. And that means that the concepts that we learn, even though it's approximate, it's pretty good. This intuition, this probabilistic intuition, if you think about it, takes us to this notion called probably approximately correct learning, PAC learning. We're going to have an approximately correct concept, but we can't be sure that it's approximately correct because we don't get to see the future. So we are probably approximately correct. PAC is one of the big pillars of learning theory, and we'll encounter PAC in a fair amount of detail when we talk about this in our module on computational learning theory. There's a comment about, is this basically the design for the common case applied to ML? Learn the common case. You can think of it that way. It's learn the case that occurs that you have seen and hope that this is a representative of the future because you don't get to see the future. The other direction that we can go is to think about online or mistake-driven learning, where we encounter a stream of examples. Like imagine that this list of examples was provided one at a time to the learner, this list. So we encounter a list of examples and we make updates to our hypothesis only when we make mistakes. If there are no mistakes, there's no reason to change our hypothesis. And every time we make a mistake, we update our hypothesis so that we correct ourselves based on what we just saw, based on the mistake we made. And we define the notion of good as in terms of the number of mistakes we make before we can declare that learning is successful. So this style of learning is called mistake-driven learning, and the goal in that case would be to quantify mistakes. All right, so I'm going to pause here. There are only 2 minutes left, and I don't want to start a new topic on online learning or mistake-driven learning. So we'll start that on Tuesday. So we can spend a couple of minutes on questions. What does overfitting look like in PAC? That's a good question. So what happens in PAC with overfitting is you will essentially memorize the fact. Overfitting is always something like memorization or rote learning, where in PAC, what happens is your learner memorizes all the training examples it has seen, and it does not allow for the possibility of any change in the future. And this could manifest itself in different ways. One easy way is we are no longer in the world of perfect data. We have noise in the data. So the learner ends up memorizing the noise in the data also. Another place where this could happen is where the learner is the hypothesis space is so large that it really it has the capacity to remember the ground truth label for every example it sees, including examples where either the label or the features are noisy. So overfitting looks pretty similar across all domains. In fact, you can always think of overfitting as memorizing the training set or memorizing some data. In general, well, rote learning is bad. Um, yes, both for humans and machines. So rote learning is not the ideal thing to do, simply because what happens with rote learning is you don't generalize to previously unseen settings, previously unseen examples, and that prevents us from you know aggregating the information that we've seen, the learners or us, from aggregating the information we have seen and building an abstraction that is the true function, rather than just sitting at the low levels, the low level of data points. The goal of learning is to uh, discover the abstraction. There is this comment about grade school being mostly rote learning, and I'm going to use moderator's privilege or instructor's privilege and say that, I don't have a comment on that. And we are out of time also, so that's also convenient. We can talk about that, Anthony, if you want offline. We should wrap up. Don't forget your homework, and watch out for a new homework late tonight or tomorrow morning. All right, I will thank you all. I'll see you on Tuesday.